Okay, great. All right. Good morning, everyone. Is the recording on? Yes. So we have a day, we have a long week ahead of us. And what I'd like to do today is introduce a very powerful tool for reasoning about undecidability problems. So we did the explicit proof that the halting problem is undecidable, and we did it by an explicit diagonalization. The proof was in the same spirit as Cantor's diagonalization argument. So we showed that if you had a thing that solved the halting problem by putting in the negation in the right way, you could make a self-contradictory program. So that's a very explicit proof, and it's a clumsy way to do undecidability proofs as things get more and more intricate. So a much preferred tool is the tool of reductions, which basically says, if I can solve this problem, then I can solve this problem. But then this problem I know is impossible, so that one must be impossible. So there's an old joke about this concept of reduction. So in mathematics, one loves to use the phrase, and we reduce the problem to one that we've already solved. The idea being that, you've shown that you've transformed the problem you're trying to look at into one that you've already solved, and that since you've already solved it, you've now solved the new problem as well. So the story goes, you have a mathematician in a hotel, checked into a hotel room, and before they give him the room key, they ask him questions to make sure he can handle emergency situations. So they say, right, there's an empty bucket in your room, in your bathtub, and you wake up in the middle of the night and you find a small fire in one corner of your room. What do you do? So he says, I rush to the bathroom, I fill the bucket with water, and I put out the fire. He said, okay, very good. Then they said, okay, question 2. You're asleep in your room, you wake up in the middle of the night and you find a small fire in the corner of your room. You rush to the bathroom and you find the bucket is already filled with water. What do you do? So they said, I empty the bucket into the tub, and it has now been reduced to a problem I've already solved. So this is the spirit of how reduction works. So let me spell out. So I've given a lot of notes, maybe 5 sets of notes for today's lecture, all on the website. So everything I'm going to scribble here is actually written in detail there, so you don't necessarily have to scramble to write everything. But let me introduce basic terminology. P reduces to Q, reduces to Q, where P and Q are problems. And this means if I can solve Q, I can solve P. And roughly speaking, this is equivalent to saying Q is harder than so if Q is harder than P and you know how to solve Q, well, you can certainly solve P. Okay, and we tend to write this like that, suggesting that somehow Q is bigger, harder, more difficult to deal with. And how do we prove these reductions? We show, so the basic scheme for doing any of these reduction proofs is like this. You notice this is a conditional statement. If I can solve Q, I can solve P. I'm not required to explain how I'm solving Q. It's just a magic gadget that supposedly solves Q. I don't have to explain how it works. In fact, most of the time, such a thing doesn't actually exist. And we're going to actually use this for contradiction proofs. So the scheme is like this. What are we required to do? We want to construct an algorithm for solving P. And so we feed in an instance of P. Okay, so how does this algorithm for P going to work? So what we do is we transform the problem. And this has to be an algorithmic transformation. Transform the instance into a Q problem. So now it's a problem for Q, and you feed it to your Q solver. How does the Q solver work? No idea. No idea, don't care. It's an assumption that it exists. And so if you've done this transformation correctly, your Q solver will answer the question for P. And so this will be a solution for P. Now, supposing you already know, if you know P is actually undecidable, then the putative Q solver cannot exist. So Q is also undecidable. Okay, so this is the logic, and this is where people tend to tie themselves in knots. They end up proving things in the wrong direction. They end up assuming that with a P gadget you can solve a Q problem, but that's not how it works. P is a problem you already know is undecidable. You want to show that Q is undecidable, and you show that I can take any P instance of a P problem, transform it into an instance of a Q problem in an algorithmic way. And if I could do that, then my putative Q solver would solve the P problem. But we know that's impossible. So the Q solver cannot exist. Okay, so we're going to start with the halting problem, but then notice this thing really is a preorder, which means transitive. So reductions can be chained. Okay, and it's not everything has to be reduced to the halting problem. What happens is that you build up your stockpile of unsolvable problems, and then when you're confronted with a new one, you look around and see which is the one most convenient for constructing a reduction. And so now, by now, nearly 100 years later, we have a nice collection of unsolvable problems. Many things are known to be unsolvable. So the halting problem for any of those things equivalent to Turing machines is unsolvable. And we can use whichever one is convenient for us. So quite often people say, oh, I'll show that the halting problem for two stack machines is can be reduced to the problem I'm looking at, and things like that. Okay, so it's not always halting problem. So this is the key point. If you know P is undecidable, then the Q solver cannot exist. And I don't have to explain. People keep asking me, but how do you have a gadget like that? And the whole point is I'm trying to explain there is no gadget to solve Q. Right? Okay, so let's do some very simple reductions. So until the break, we'll do simple reductions, and then we'll start doing not so simple reductions. We'll also start seeing the first traces of the hierarchy of degrees of unsolvability. You'll see that not everything is just solvable, unsolvable. It's actually more and more and more unsolvable problems, meaning more difficult than the original ones. So let me introduce some notation first. So I'll use this to mean encoding of a machine. What do you mean encoding? the point is, and this is one of Turing's fundamental contributions, programs are data. And we are so used to this, we think nothing of writing software, which is, after all, just a string of characters. Okay, but it is also a program. So a Turing machine, you can somehow code it up as a string. Strings can be coded up as integers. So whichever way is convenient for me, I will pretend I have the thing coded up as an integer or a string or whatever I want. But I won't even care about how I'm encoding it or what the encoding is. So I'll just write angle brackets around M to mean encoding of M. And sometimes I'll write things like this. So this is a machine and a word. And sometimes maybe two machines. Or maybe this encoding of a CFG. Okay, so I'm going to prove undecidability results about context-free grammars later on. So in every case, we'll just say, I've got an encoding, I can decode it. And the encoding and decoding are always assumed to be algorithmic, but we know very well how to do all these things. So first one, I'm going to define. So I'm going to think of these things as languages. So HTM is the set of strings. So you see, this is a set of strings. What kind of strings? The strings are encodings of a Turing machine and a possible input word. Such that the machine actually halts on that word. So that's just some set of strings. Similarly, we'll talk about ATM, which is another language. M accepts W. Okay. Sometimes I'll say, oh, I'm thinking of this as integers today instead of strings. It doesn't matter. We know we can just go back and forth. We've done enough bijections between integers and pairs of integers and so on to see that any finite thing can be coded up as an integer or a string. Any string can be coded up as an integer. Any of these encodings, decodings are all totally computable. Okay, so let's do the first of our reduction arguments, HTM. And intuitively, this is clear. If I could solve the acceptance problem, then definitely I could solve the halting problem. So, but let's do it. This is a very easy one. And it's more for making sure you understand the logic. So what are we trying to build? We're trying to build an algorithm for the halting problem. So what's an instance of the halting problem? An encoding of a machine together with a word. And now what do we do inside? So this is the thing that needs to be spelled out with some care. So here's what we're doing inside. We will construct M prime. And we do this a lot, and people have also a hard time understanding what you mean by construct a machine. I mean, write the code off. So constructing a machine is not the same thing as running a machine. Writing a program is not the same thing as running a program. So construct M prime, and this is the description of the behavior of M prime. It's not running M prime. It's how does M prime work? On input X, simulate M with X. If M halts on X, accept it. Okay, so it's a slight modification of the machine M, right? It says, okay, I'm going to basically run the machine M, but at the end, if it goes into a halting state, I will not care whether it's accept or reject. I will basically change my reject state to an accept state. So whenever the first machine actually halts, it'll accept. So now I will ask my gadget. So let me make this thing in red. So here is some algorithm for accept TM. And I will ask this. So I'll feed it M prime and W. So if this thing says M prime accepts W, then I know the original machine halted on W. So this solved the halting problem. So the algorithm for ATM cannot exist. Okay. Of course, we could have directly proved that the problem for ATM is undecidable, very similarly to the way that we did it for HTM. And after all, these are very, very closely related problems. So we can actually do both reductions. This is why I didn't say that the reduction relation is a partial order, it's a pre-order. So ATM also reduces to HTM. And how are we going to prove this? Well, we feed in an instance for ATM. We're going to construct an algorithm for ATM. And we're going to use our halting gadget to solve it. And we directly feed this to our algorithm for HTM. Somehow it's supposed to magically work and solve the halting problem. We don't know how it works. We don't care. We assume we have such a thing. And now our algorithm for the halting problem will have one or two responses. It may say yes, or it may say no. So if it says no, so it outputs false, it says M does not halt on W, then just reject W. Because obviously if it didn't halt, it couldn't have not have accepted it. And then if it says true, it halts, then simulate M on W and say whether and check if it is accepted. And you can output the answer yes, no. Okay, so basically the halting, magic halting gadget takes care of the difficult case when the thing might not have halted. But wait a minute, we know the acceptance problem is undecidable, so certainly the halting problem should also be undecidable. So every time I'm drawing one of these gadgets in red, this is pure science fiction. I'm assuming that if I had such a thing, then I could build this gadget shown in black, and I get something that we know couldn't, or shouldn't exist. Okay, so let me stop here and ask if anybody is having problems just with the logical structure of these arguments. They're extremely simple constructions. So my experience was people had a lot of trouble wrapping their heads around the logic of these things. And typically they would ask me, but I don't see how you had an algorithm for HTM. And that question simply indicates you don't know what the word if means. If I had a gadget for solving the halting problem, then I would have a gadget for solving the acceptance problem. So if that aspect of conditional statements is clear to you, it should be clear. But anyway, let me see. Rosie, are you checking the chat? Nobody has questions?
No questions.
Okay. So these were perhaps unexciting reductions because acceptance and halting already so close. You're probably not shocked by this. So let's start getting more problems and also studying getting an intuition for the degree of difficulty. So I'm going to introduce a new language now. It's called empty. And this is the set of strings which represent encodings of Turing machines such that the language of the Turing machine is the empty set. In short, nothing is accepted. Your every intuition should be telling you this is undecidable. In fact, it should tell you this is more undecidable. And that's a good intuition because that's actually technically correct. But we don't yet have the language to say how much more undecidable. But for now, we're not going to worry about that. We're just going to prove this is undecidable. And we're going to do this reduction. Okay, so let's make a first try. Based on the kinds of things we did before, which were very naive and simple. There was nothing really fancy going on. So first question I want to ask, what are we trying to do here? An algorithm for what?
For ATM.
Very good. So we want to build an algorithm for solving the acceptance problem. What does an instance of the acceptance problem look like? An encoding of a machine and a word, and its output at the other end should be, does M accept W? Inside, we can try and do what we want, but we get to use a magic gadget that solves the emptiness problem. So inside, we'll say, okay, what we have here is a magic gadget that solves the emptiness problem. So we feed it M, we ignore the W. So of course, all these things are computable encoding. So I can decode MW, I can take out the W part, re-encode it as just M, and I can feed that M. And so if this thing says yes, then we say, okay, no, because our magic emptiness gadget says this doesn't accept anything. So it certainly doesn't accept W. So we can safely say no. And what if this thing says no? Well, the emptiness gadget said the language of M is not empty. It didn't say W is in this set or not. So we are kind of wondering, geez, now what do we do? So this doesn't actually get us very far. And this whole idea doesn't work. So let's try again. As you can see, the gadget had to be a bit more complicated, so I gave myself a bit more space. So we're trying to construct an algorithm for ATM. Okay, good. What's an instance of ATM? A machine and a word. And we want to know, did M accept W or not? Okay, So inside, we're going to build a new machine. Okay, so here we say, design a new machine. And what does it do? So this machine is called M prime. Input is called X. Okay, so remember, this is the code for M prime. I'm not running M prime, I'm just building the code for it. This is a point that people repeatedly fail to grasp. At no point did I say I'm running M prime. I'm just saying I'm writing code for M prime. So what does M prime do? Step one, it asks, is X equal to W? And two, if no, then just reject. Then three, if yes, simulate M on W and accept X if M accepts W. So obviously, if you're running this, then at this point, M might just loop on W, in which case, obviously, you're not accepting it. So this is the code for M prime. At no stage am I running it. But now I feed it to my magic gadget shown in red. And this is somehow able to answer the question, is the language of this machine that you're giving me as input empty? And you get some answer. But what I do with that answer is I flip it. So if the machine says, yeah, the language is empty, why do I flip it? Sorry, I don't flip it. I just feed it out. So here's the point. If M accepts W, language of M prime is W. If M does not accept W, language of M prime is empty. So sorry, yes, we should flip it because this thing is answering yes for empty. So yes for empty means no for it accepted W. And no for empty means yes, it accepted W. Okay, so small modification, this new machine M prime has this property. Its language is empty if and only if M does not accept W. So if this magic machine can answer the emptiness question, the overall machine answers the acceptance question. But acceptance question is undecidable. So emptiness question must be undecidable. Okay, so empty TM must be undecidable. All right. Let's raise the stakes a bit. But I mean, intuitively, you should expect that, right? I can't even tell if the specific machine halts on this or accepts a specific word. Now you're asking me, does it accept any word? So that's obviously a harder question because I have to somehow search through all possible words. But now we're going to ask slightly more subtle questions. So Turing machines are very powerful things. the most powerful computational devices, we think. And so but it could be that the Turing machine that you built is actually accepting a simple language. So we're going to ask I've got a Turing machine M and I'm wondering, so it's accepting some language, but is that language regular? Okay, so that's their question. Is this thing a regular language? And this is undecidable. So we're going to show, so we'll call this thing reg. Okay, so now we're going to do a reduction of ATM to reg, which means, hey, if you can solve reg, you can solve the acceptance problem. But then acceptance problem is undecidable, so it should not be possible to solve reg. So here we go. So what are we trying to construct? An algorithm for ATM, not an algorithm for reg. Algorithm for reg is magically given to us. Somebody Amazon has delivered this box that says inside is a machine that tells you whether the encoding of a Turing machine defines a regular language. And we're going to now wire that up to some simple other things that we already have and magically build an impossible gadget. Okay, so encoding of a machine and a word. And we want to know, does the machine M accept the word W? Okay. And here's what happens inside the box. Maybe I should make this a bit thinner. All right. Is this blue visible to all of you, or is it too faint? Yeah, okay. So we're going to build a new Turing machine called M prime. And its input is going to be called X, okay, to distinguish it from M and W. This is a new machine M prime, and the parameter for that machine M prime, I'm going to call it X. And of course, what I'm showing below is not M prime. I'm showing you code for M prime because it's this code that I'm going to feed to my reg tester. So we're going to check, is X equal A to the N, B to the N? Turing machines can do this in their sleep, right? If yes, then accept. Accept X, that is. 2, if no, so X is not of the form A to the N, B to the N, then simulate M on W, not on X. Simulate M on W. If M accepts W, then accept X. So you see the code for M is hardwired into the code for M prime because it can run a simulator of M. And now we feed not M prime, but the code for M prime into our supernatural gadget, which is somehow able to answer the question, is the output regular? And let's analyze this situation now. Suppose M accepts W, then what's the language of M prime? Well, if you look at the code, you'll see if X is of this form, we've accepted it anyway. And if X is not of that form, then all we're running is the simulator for M. And if it accepts W, we accept X, whatever it is. So that means we're accepting every word. So the language of M is sigma star. Language of M prime is rather is sigma star. If M does not accept W, then what's the language of M prime? By the way, remember that does not accept W doesn't mean it rejected W. It could have gone into a loop as well. So if M does not accept W, what's the language of M prime?
A to the n, b to the n.
Exactly, because that you accepted right off the bat before even running the simulator. And after that, it's not accepting anything except that strings that it saw in that first phase. And you see, this is a regular language, but this one is not. And our magic gadget is supposed to be able to tell that. So if it says, yeah, it's a regular language, then you know it accepts, M must have accepted W. And if it tells you, no, it's not a regular language, then you know M did not accept W. So you've solved the acceptance problem. So reg is undecidable. And again, you should kind of expect this. This is like surely a much harder question because I'm asking you something about all the words that it accepts. And sure enough, when you see that the question is much harder, you'll see that the reduction is a lot easier. Because you're saying, give me this super powerful gadget, then yeah, of course I can solve the halting problem easily. If it's a long and complicated construction, then maybe it's just about as difficult as the halting problem. Okay. Now we come to the next level of difficulty, so to speak. I'm giving you two machines, M1 and M2, and I want to know, is the language of the first machine equal to the language of the second machine? We'll call this EQ, or equality. So it's not that the machines are the same. Completely different machines might be doing the same thing. And you're used to this. Completely different programs do the same thing, right? Insertion sort and merge sort, both sort. But the code is totally different. So I'm giving you two machines and I'm wondering, they might have completely different internal structure and work in different ways, but in the end, maybe they're accepting the same language. And so this is the encoding of pairs of machines, M1, M2. Both of them are coded up and packaged as a single string or integer or whatever it is. And I'm asking this question, is the language of M1 equal to the language of M2? So this is called the equality problem. And if you think that this is going to be possibly decidable, your intuitions need to be checked because this is obviously a very difficult question. And later on, we'll see that it is more difficult than the halting problem. But right now, we're going to prove that this is undecidable, and we're going to do it by a reduction argument. But we're not going to the halting problem anymore. We've built up a bit of a stock now. We've got reg, we've got empty, we've got ATM. So why do we always have to use ATM? No, we're going to use empty today. So we're going to do this reduction. And it says, hey, if you could solve the equality problem, you can solve the emptiness problem. So this is actually a ridiculously easy. So what does the input for the emptiness problem look like? It's the encoding of one Turing machine. And it's asking, does this thing accept anything or nothing? Right? So to say a yes answer means it doesn't accept anything. Every single word it rejects, all loops. Okay. So what do we put inside? So define M prime, which rejects its input immediately. That's it. Very simple machine. Ignores its input, goes right to reject state and stays there and says, I'm rejecting. I don't care what the input is. Easy machine to define, easy to get the code, easy to unpackage the code for M and repackage it together with the code for M prime. So now I've got this coded pair and I'm going to feed it to my gadget that somehow is able to answer equality questions. So answers the equality question, yes, no. It says, yes, they're equal. Well, M prime by construction accepts the empty language. And so we just take the output unmodified and say that's our answer to the emptiness query. And you can clearly see this work. The languages of M and M prime are the same if and only if the language of M is empty. If and only if was important. So some exercises for you to do. I've written these in the notes, but you can see them here as well. Show that the language of this question is undecidable, where M prime always holds. We somehow are giving you a M prime that always holds. I'm asking you, is the language of the Turing machine context free? So that's a bit similar to reg, very similar in fact. These are like all, in some sense, 3-minute exercises, not 45 minutes of staring. This may be a bit longer. Show that the language of M is finite. And 4, show that the language of M is sigma star. So all these are, show all these are undecidable. Okay, so I can do them all for you. 3 minutes each, really. But I think you learn more doing them yourself. And they're all in the same spirit of things I've already done. So the thing I want to emphasize is that this is nowhere near like as complicated as reductions you might have had to do for proving NP completeness. So these are all kind of simple arguments, but it's the logical structure that tends to confuse people. Okay. So let me take a 60-second break in case anyone has a question or is feeling dizzy. So I've been not 100% precise about what I mean by reduction. I've said you assume you have a gadget for solving this question, and then you somehow construct a gadget for solving that question. And what am I allowed to do in that construction, in fact? So let me make it more precise. So the notion of reduction that we've had so far is what's called Turing reduction. And I'll say more precisely what Turing reduction is in a minute. But before I get to Turing reduction, I want to make a sharper notion of reduction. So this is a new subtopic, a sharper notion of reduction. And this is called mapping reduction. So this is very nicely explained in a book by Michael Sipser. And I'm sure many of you have already downloaded illegal copies of it. So Sipser's book was the text I used to use for this course. He calls it mapping reduction, and I think this is a very good name. In the general literature, it's called many-one reduction, and I never understood, like, what is the point of calling it that? It's a silly name. So the big advantage of mapping reduction and many-one reduction is that they both have the subscript M, so at least you can read the notation everywhere, it'll mean the same thing. But let me define it carefully. Suppose L1 and L2 are languages. Okay, so we can equally well talk about reductions between algorithmic problems and reductions between languages, because we've shown that every algorithmic problem can be cast as a language problem. Then we will say L1 is mapping reducible to L2. And we'll write L1 with a little subscript M there. If there exists, please note this is a quantifier. It's an existential quantifier. So I have to find one thing like this, not 1700. If there exists a total computable in case you've forgotten what that means, an algorithm that always halts. Okay, a total computable function, f from sigma star to sigma star. So it can accept any string as input. It's guaranteed to halt, and it's guaranteed to be a computable function. So it's no black magic in it. There's some algorithm and you know it's going to halt, such that for all words in sigma star, that word is an L1 if and only if f of that word is in L2. So this is a groovy thing, because it says, gee, I want to figure out an algorithm for whether a word belongs to L1, and you say, but I've got this f. I've mapped it. I've mapped W to f of W, and now I know that if f of W is in L2, then W is in L1, and it is an if and only if. So to reiterate, 1, if L1 mapping reduces to L2, then L1 complement, mapping reduces to L2 complement. This is absolutely not true with general reductions. And 2, this mapping reduction concept has a direction. You might look at that if and only if and say, oh yeah, well, gosh, it's a bidirectional thing, but it's not. Because F has a direction. So you can translate questions about L1 into questions about L2. You have no guarantee that you can translate questions about L2 into questions about L1 because nobody told you that F is surjective. So if you have a word that's not in the image of this F, this is not going to help you. Okay, so L1 does, let me make this both bold and red, does not mean the same as L2. Okay, so please keep this in mind. So there we are, cruising along on mapping reductions. So let me tell you some fundamental facts about mapping reduction. So mapping reduction is super useful, but not always possible. Okay, fact 1. Supposing P, I defined it for languages, but languages, problems, machines, these are all interchangeable things. If P is mapping reducible to Q and P is undecidable, then Q is undecidable. Not all the reductions that I've shown you so far are mapping reductions. Some of them are, and some of them are not. So I'll clarify which ones, or rather I'll let you clarify, but I'll give you in a more sharp way what is the precise difference. If P is mapping reducible to Q and Q is decidable, then P is decidable. So that's great. It can actually be used to show a decision problem. Okay. Now remember what I said about computably enumerable. So that's kind of one level up. So computably enumerable means I have a machine that outputs all the things in the language in some order. If your thing is in the language, you will eventually see it and you'll know, yes, it's there. If it's not there, you'll never know because you might be waiting, wondering, is it going to come later or is it just not there? Okay, so an enumerator just spits out the things. It spits it out in some unpredictable order so that you cannot just tell, oh, it should have come by now. Okay, now this is also called a semi-decision problem. So a semi-decision problem is one for which if the answer is yes, your algorithm will tell you. If the answer is no, you don't know. Maybe it'll say, give you an answer, maybe not. Okay, but if the answer is yes, it will definitely give you. So what's an example of this? Well, the halting problem. And what's the algorithm? Run the damn machine. And if it halts, you'll find out and say, oh, it halted. And if it's not going to halt, you'll say, I don't know, maybe it's going to halt, maybe not. Okay, so that's a typical example of a semi-decision problem, also called a computably enumerable set, the set of such things that are accepted by a Turing machine. is always a computably enumerable set. Okay? So if P mapping reduces to Q and Q is CE or semi-decidable, then P is also CE. And that's because the F that does the translation is guaranteed to halt. So you know you're going to get to run your Q machine on it. So it's not just at the undecidability level, but also at the computably enumerable level, you can transfer information using mapping reductions, which you can't do with Turing reductions. So supposing I know that P is mapping reducible to Q, and I know P is not CE. So maybe worse than computably enumerable, then Q cannot be CE. If I have a mapping reduction like this, and P is not co-CE, then Q cannot be co-CE. So co-CE means this. If the answer is no, your algorithm will definitely tell you. Whereas CE means if the answer is yes, your algorithm will definitely tell you. Okay, please give me an example of a co-CE set, which I've already shown you.
Rahul asked if COSI means a complement to CE.
Yes. Which is spelled COMPLENENT, not PLI. So HTM and ATM are CE. If you want to know whether it halts, run it. If it halts, you'll definitely find out. Same with acceptance. CE, but not co-CE. So give me an example of something that's co-CE.
Like the complement of those two.
Very good. Exactly. So I give you a Turing machine and a word, and I say, please tell me if the machine does not accept this word. So if the answer is no, which means the machine does accept the word, then you'll find out. But if you're waiting for a no answer, okay, so this is a typical co-CE problem, but another one is empty. Right? Because you dovetail through all possible words. And if there is some word in there, eventually the machine, through the dovetailing process, will halt and and accept it. And then you'll say, it's not empty. So if the answer is no, we'll definitely find out. If the answer is yes, it's empty, you might be going and saying, well, so far it hasn't accepted anything, but how do I know? Maybe later on it's going to accept something. Okay, so these are crucial concepts. And of course, complement of empty is CE. So remember, we proved ATM had a reduction to empty, but this is not a mapping reduction. Why? Suppose we had a mapping reduction. To empty. Then this also holds, right? But this is not possible because this is co-CE, not CE. And complement of empty is CE. So this is not possible. So here's a reduction which is not a mapping reduction. So what's the difference? So this thing is called Turing reduction. I get to use Q as many times as I want. So let me make this clearer. I get to use Q oracle. So we just have this magic oracle that you can ask at any time for a Q question, and it'll say, yeah, here's the answer immediately, like the oracle at Delphi. So I get to use a Q oracle as many times as I want. And I can do any computable post-processing. I want. So I can ask my Q oracle a question. I can take the answer. Based on the answer, I can make some construction, do some calculation, ask the Q oracle something again, get the answer, do some more calculations, ask a third time, get the answer, do another calculation, and then output, and then say, yeah, this is my answer to the P question. So this is called Turing reduction. And all the things about if P is undecidable, then Q is undecidable apply. Okay, because everywhere I'm doing computable post-processing. But this means I get to do some total computable pre-processing. Then ask my QOracle 1 question. And output the answer without post-processing. Can't even flip the answer. So because mapping reduction is so much more strict than Turing reduction, it gives you much stronger guarantees. That's why it really preserves where you are in the computability hierarchy. Whereas Turing reduction is a much cruder tool, but the whole collection of Turing problems is very difficult. Okay, so I want to do, so I'm going to show you a statement which I'm not going to prove because it's carefully written up in the notes, and I want you to read it. The reductions are simple because I do want to show you a one slightly novel reduction, because all the reductions we've done have had, now you've seen several of them and they're kind of all starting to look the same, right? But I want to show you a somewhat novel reduction. Okay, so this one is not novel, but worth knowing. EQTM is not CE nor co-CE. And basically, you can prove reductions to both ATM and ATM complement. In fact, mapping reductions. So it tells you, hey, this guy is higher up there. Okay, the reductions are easy. They're worked out. But just so you get, so I'm warming you up for a topic where I'm going to show you the whole hierarchy. There's an infinite hierarchy of increasingly difficult problems. So already this is a hint. EQTM is kind of more difficult than either the halting problem or the non-halting problem, or the accept problem or the non-accept problem. So there is a notion of completeness. So in fact, the halting problem is complete for all CE problems. Namely, if you could solve the halting problem, you can solve any CE problem. So it's in fact CE complete. Now, of course, the non-halting problem is not CE. Okay, so if you could solve the halting problem doesn't mean you can solve the non-halting problem. So those things are co-CE, but the non-halting problem is co-CE complete. If you could solve it, you could solve all co-CE problems. And you might think, well, that's it. There's CE, co-CE, and remember, if something is both CE and co-CE, it's decidable, right? Because you run the two things in parallel, and one of them has to give you an answer. Okay, so in fact, this thing goes on infinitely. So it shows you EQTM is neither CE nor co-CE, so somewhere higher up, and in fact, there are infinitely many levels. Going down a bit, you can ask another question. So it turns out all the undecidable problems we looked at, they're all CE complete or co-CE complete. And so you might say, oh, well, maybe it's decidable, and then the next jump is CE complete. And is there something in between? So not as difficult as the halting problem, but still undecidable. And this turned out to be super, super difficult. People said, yeah, how do we do this? And finally, I think it was in the late 1950s. So, you know, like 25 years after people started studying these questions, that it was solved by two young grad students independently, one in the Soviet Union called Muchnik and one in the United States called Friedberg. And they were both such babies that they were called the Friedberg-Munchkin theorem, even though it should have been called the Friedberg-Muchnick theorem. And they invented a whole new technique called the finite injury method. It turned out to be very complicated, but they finally showed that there were problems that are kind of in between. But there are no kind of natural problems that are in between. But higher up, yes, there are. Okay, so I want to show you one more reduction of a slightly different nature, and it's more in the CoCE world. And so here's the question. I have a Turing machine M, and I want to know that it accepts infinitely many words. So the language is called INF. INF is the set of encodings of Turing machines such that the language of M, the size of that language is infinity. So I claim that we can do this. Okay, so it doesn't mean that INF is CoCE, might be worse, but it's at least CoCE, and it's definitely not CE. But what's interesting is it is a chance for me to show you a different kind of reduction trick. So I'm not going to draw those boxes and all anymore. I'm just going to show you how the reduction works. So we are given MW, and we want to know, does M loop forever on input W? Okay, so you see, this is not the halting problem, it's the non-halting problem. I want a yes answer if it loops forever, and I want a no answer if it halts. So I claim that if you could solve inf, well, certainly that's undecidable. Because if it was decidable, then the halting problem would also be decidable. So certainly it's undecidable, but it's a different kind of undecidability. And inf is like that. So the halting problem, the non-halting problem is not CE. It's in fact CoCE. Okay, so define M prime as follows. Remember, I'm defining it. This is one of the examples that confuses people. They say, but how can you do that? Won't it run forever? But I'm not actually running it. I'm just defining it. Okay. So input to M prime is X, not W. W is the input to our original M thing. And we want to know if M loops forever. But we're building an M prime to answer this question. So here's the code of M prime. 1, simulate M on W for length of X many steps. So X is a string, it has some length, maybe the length is 300. You run M on W for 300 steps. Turing machines have a well-defined notion of what a step is. You read a cell, you do a transition, you move the head one step, and maybe change the symbol. That's one step. So you can count steps in an unambiguous way. Okay, so if the length of X is 3, you just run it for 3 steps, that's it, and then you stop. And now, if M halts on W before the end of the simulation, reject X. else, I don't know why I wrote a 1 there. This is the only thing in the code. Else except X. Remember, I screamed and yelled and waved my arms frantically, and I said, you can't say, run this thing, and if it doesn't halt, do something. But now, of course, this is not the same because it's a bounded simulation. I'm running the simulation for some fixed number of steps. Either it halted in that time or it didn't, and I will know for sure. So either halted within that many steps or not. Okay, so now let's do some analysis. If M does not halt on W, then the language of M prime is infinite, because it'll actually accept everything, right? Because no matter how many steps you tell it to run the simulation, it will be running M on W, and since M doesn't halt on W, it'll say, nope, hasn't halted yet, so I get to accept this X. So in fact, the language of M prime in this case is actually sigma star. In fact, the language of M prime is sigma star. If M halts on W after n steps, M prime rejects all words X such that length of X is greater than n. So in this case, the language of M prime is finite. So I didn't have to do any post-processing. I just say, whatever my inf detector said, that's my answer. So this is really a mapping reduction. It's a computable construction because I can certainly write this code. This simulate M on W is, you just take the code of M and run it on my interpreter. Okay, and so this is a different kind of reduction, as you can see, because it did a reduction to the non-halting problem. And it did this trick of keep running the simulation, but cut it off at a certain length. Okay, so this is a bit of a nifty little trick. And now I'm going to show you a theorem called Rice's theorem. And then we'll have a break. And then I'll do, for the first time, a rather complicated reduction, which will take a good 35 or 40 minutes. Okay, so let prog is the set of all programs in some language. Turing complete. Okay. So in fact, the set of valid programs in a language is a decidable set. This is why we build parsers. Okay. for simplicity, I'm going to assume all programs take one integer input and produce one integer output. So I'm going to assume the type is for all of them n. Okay. So every program P defines a computably enumerable set. So P belongs to prog. It's a possible program, and it will have this type, and it defines a set. So I'm going to think now in terms of integers rather than in terms of strings, but as I told you, never doesn't matter one bit. So P defines a set of pairs. Namely, that's the output if I run P with input X, the output will be Y. And when I write P of X equals Y, I mean P halts and produces Y, terminates. If it doesn't terminate, there's no output. So in fact, these should be, technically speaking, partial functions, though we don't usually write things like that in our type system. Okay. Okay, so now I want to explain an important concept. So I'm going to define an equivalence relation. P1 is equivalent to P2 means P1 the input-output relation is exactly the same. Okay, so we say P1, P2 are extensionally equal. So we can think of this in terms of Turing machines if you want. So we will say a map Q from prog to the Booleans is called a property of programs. Okay, so to every program it says yes, yes, no, no. So it's just a property. Some of you have it, some of you don't. So every property is just some Boolean valued function. We say Q is an extensional property. If when P1 and P2 are extensionally equivalent, then either they both have the property or they both don't. In short, Q only depends on the IO behavior. In the world of software engineering, Q only depends on the functional spec. Clear? So what are examples of extensional properties and not extensional properties? P is a sorting algorithm. That's an extensional property, right? Other sorting algorithms may have totally different ways of working, but they're sorting. It only depends on the IO. Running time of this algorithm is cubic, not extensional, because you could have an n-squared algorithm that's doing exactly the same IO thing. This algorithm has 100,000 lines of code, not extensional. Okay, so all those things are not extensional properties. They're called intensional properties. Anything to do with performance, the actual text and so on, those are intensional properties. Extensional properties only depend on the functional spec. Okay, so now let me define something called a trivial property. So Q always true, or Q always false. So if I just say one of my properties is that every program has this, satisfies my property. So that's a very, very liberal property. The other one is on the other extreme of stringency. You say no program satisfies this property. I don't even have to look. Okay, these are trivial properties. Obviously, the trivial properties are decidable. What's my decision procedure for the trivial true property? I don't look at the program, I just say true. What's my decision procedure for the other one? I don't look at the program, I just say false. Okay, so obviously those are decidable. What about the ones in between? We call them non-trivial properties. Every non-trivial extensional property of programs, or you can equally say of CE sets, is undecidable. So this is kind of it's actually a simple theorem to prove, but it's a mind-blowing thing. It says, don't worry about screwing around with doing this reduction and that reduction. Just forget it. They're all undecidable. Anything you wanted to do in your compiler class, undecidable. No, that's not true. Some things are decidable, but nothing extensional. This is the point. Nothing that just depends on the IO spec can possibly be decidable. Okay. Let Q be a non-trivial property of CE sets. I'm going back and forth between calling them CE sets and calling them programs. Doesn't make a difference. So what does it mean to be non-trivial? There exists some P such that Q of P is true, and there exists some P prime such that Q of P prime is false. So not all true and not all false. Some true, some false. So assume empty does not satisfy Q. I.e., for any M, if the language of M is the empty set, then Q of M is false. And this is a harmless assumption, because if it's not the case, I just use not Q as my property. So without loss of generality, I can do this. Let M0 be such that Q of M0 equals true. Of course, language of M0 is not empty by our assumption. So define LQ to be the set of machines such that Q of M equals true. All the things that satisfy Q. And we have assumed that Q is an extensional property. Okay, so we're going to show ATM mapping reduces to LQ. Okay. So we're trying to construct a solver for ATM. We've got a gadget that solves LQ. So our input is MW, an instance of the problem for the acceptance query. We have a gadget to solve X in LQ. This is a decider. Okay, so now we construct M prime. So input for M prime is X. So how does M prime work? 1, simulate M on W. 2, if M accepts W, then simulate M0 on X. That's all. You notice I don't have an if then else, because M doesn't accept W. How do I know that? Maybe it's going into a loop. So for a semi-decision procedure, I can use M accepts W in the then branch, but I dare not put in an else branch. Okay, let's analyze this. We feed the code for M prime to our LQ gadget, which, remember, is a decision procedure. It's supposed to answer that. Now, notice, if M accepts W, then language of M prime equals language of M0, right? And Q of M prime is true. Why? Since Q is extensional. It's an extensional properties. If they agree on the language, then that's it. They both satisfy the Q or they both fail. But we've chosen M0 to satisfy Q. So M prime certainly satisfies Q in this case. If M does not accept W, this, by the way, this is our meta reasoning. It's not like the algorithm is saying if doesn't accept Q, then I do X, I do something. Okay, so if M does not accept W, then the language of M prime, you never get to the then branch, right? We don't get to do anything. It just stopped, and whatever happened to X is not going to get accepted. And we chose empty. So now we chose empty to be the thing that doesn't satisfy Q. And since Q is an extensional property, because M prime has that property, it must also fail to satisfy Q. So Q of M prime is false. So if you can decide whether this thing is an LQ or not, then you can decide the acceptance problem. So our LQ gadget now answers the question, does M accept W? No post-processing. It's a mapping reduction. And I just asked it once. And so that's the end of our proof. Every non-trivial extensional property is undecidable. Forget it. You don't have to do a reduction, no rice, put all to rest. Okay, we'll take a short break, maybe 10 minutes, 12:25 we resume, and then we have a tough reduction to do after that. These were all what I would call easy reductions. The post-break reduction is a reduction that will test your soul. Okay, we resume with a discussion of valid computations of a Turing machine. So this is a tool for establishing many undecidability results about context-free grammars and languages. And basically, the idea is, given a Turing machine, M, and a word, W, the set of valid computations of the Turing machine is a set. Okay, this is maybe a bad way to say it. Given a Turing machine and a word, a valid computation of the Turing machine is a string which describes the sequence of configurations from the start configuration to the end with an except state. Okay. So valcomps MW is the set of all such valid computations. If M is deterministic, there will be only one valid computation or none. Because it might be that it doesn't accept the string. It might be it just goes into an infinite loop. And so there is no proper valid computation that says start from the start state, and every successive configuration, of course, is according to the rules of the Turing machine. So is everybody crystal clear about what valid computation means? It's not an infinite string describing a looping computation. Okay, it's a finite string starting from the start configuration. Then it shows every configuration of the Turing machine, each one following from the preceding one, using the correct transition rules of the Turing machine and ending up, after a finite number of steps, in a accepting state, terminated. So there might be only one. If it's a deterministic machine, there might be only one, or there might be none because maybe it just doesn't accept this word, or loops or whatever. It might be a non-deterministic Turing machine, in which case there are many, or could be many, could be none. We don't care. So we just have this set. So here is the major claim. Even though we do not know in advance if M accepts W, we can effectively construct a push-down automaton such that it accepts valcomp's MW. Ooh. So there will be some complexity in doing this construction, but let's see what this means. Sorry, I forgot one super important thing, and I'm emphasizing it now. It effectively accepts valcomp's complement. Okay, valcomp's complement. Right. So the complement of the set of valid computations of a Turing machine is a context-free language. What does it mean if this set is sigma star? It means there are no valid computations. That means valcomps is an empty set. It means the machine did not accept W. I better not be able to test arbitrary context-free languages to see if they're empty or not. I'm sorry, to see if they're sigma star or not. And this is a massive reduction to show how that works. But it opens the door to all kinds of undecidability questions about context-free languages. Okay, so this global, if you lose track of details, it's not so important. In any case, you learn details by staring at the things, at the notes which I've written up in detail, but the logic here is crucial. The construction is effective, and I don't know in advance whether the thing halts or not. It's just by looking at the rules, I can construct this push-down automaton. Okay, ready? Okay, another thing I want you to remember is some time back, I showed you how to write a push-down automaton. I even typed this up and put it on the webpage as a special note. A push-down automaton that checks the complement of the language WW. So it said, if the language is not of the, if the word is not of the form WW, two identical copies, then a push-down automaton can detect that. Okay, so we're going to use exactly that kind of trick for this. So what does a valid computation look like? It's all spelled out in some detail in the notes, but we're going to use this as a marker to delimit successive configurations. So we're going to assume that this is not one of the letters in the tape alphabet. This hash mark is just there to tell you this configuration is ended, the next one is started. Okay. So remember how we describe a configuration. So supposing I have a piece of tape. Sorry, the tape goes on, of course. And there are some cells. And we're looking at this cell. Here is where the head is. And the machine is in state Q. Okay, so how did we represent this? We wrote this as A, B, B, Q, A, B, B, A, B. And let's say this was blank from then on. So then we stop. There's only a finite word on the tape. So even though the tape in principle is infinite, at any given stage, only a finite piece of that tape has anything written on it. So this is A configuration. And shows everything about the state of the machine, what's on the tape, what state it's in, where is the head looking at. The head is looking at cell number 4. Okay. All right. So what's the start configuration? Well, it has to be of this form. Because the machine is at the left edge. It's looking at the leftmost cell. The head is looking at the leftmost cell. The word is all to the right of it. And it's just that word. It has to be in the start state. So that's the start configuration. Okay. Now supposing, so I'm reminding you things about Turing machine. Supposing delta Q B equals Q prime A R. So then what happens to the tape? So maybe we have a configuration like this: A B Q B A B. This is obviously not that configuration. Let's say there's some machine and it's in this configuration, then it does this thing. So how does it change? So this is the cell it's looking at. So that gets rewritten to an A and it moves one step to the right. So now it's looking at the cell with an A on it. So it'll be A, B. This B got rewritten to an A. It's moved one step to the right. So it's now looking at this A that was just after that B. Okay, everybody clear how this configuration changed? Crucial fact. All changes are confined to a 3-cell window. Might be a huge big word. You might jump to any state, but the configuration can only change in a 3-cell window. So it's a very local change. Okay, good. So let alpha 0 be the start configuration. And assume for all I, alpha I to alpha I plus 1 follows the transition rules of the machine. And assume alpha n is an accept configuration. Okay, so then your valid computation will look like this. Okay, so this is a valid computation. Right. Oh. So how are we going to proceed? So I didn't say that a pushdown automaton, I did not say that a pushdown automaton can check the valid computations. In fact, it can't. It can check the complement of the valid computations. So in my notes, I used HTM rather than ATM. So let me write that, because it doesn't really matter whether you say it's in an accept state or in an accept or reject state. But a valid, whichever way you define it, doesn't make much difference. The crucial thing is that it's finite and can be checked. Okay, so we're going to do this reduction here. We're going to give a mapping reduction to the set of grammars, which there's an effective construction to go between PDAs and grammars. So I will interchangeably use whatever I feel like. I'm actually going to show you a pushdown automaton, not a grammar. And basically, if this thing does not accept the word, there are no valid computations. And so the complement of valcomps is going to be sigma star. And so if I have a thing that can answer the question, is this grammar producing sigma star? It will solve the halting problem or the acceptance problem. Okay. Now, we're checking the complement of valcomps. Okay, so let me see. To be in valcomps, MW, 5 conditions must be met. One, I guess I used A. Okay, so we're going to ask the question, is Z in valcomps MW? A, Z begins and ends with this, and between any two of these, we must have a non-empty string. Basically in the alphabet without hash mark. Okay, so you can't have 3 hash marks in a row. So I'll just write down here. DFA can check this. So what I'm going to do is I'm going to list down 5 conditions. 4 of them can be checked with the DFA. So I just run 4 DFAs in parallel to check those things. And we won't even think about them anymore. One of them requires a pushdown automaton. Okay. Each alpha I must contain exactly one state, right? Otherwise, it's not a valid configuration. You can't have 3 states. The head is in one place. I mean, so DFA can check this. I'll just write DFA. Easy. All you're saying, is there exactly one state? Say 2 states before the next hash mark, reject. I see no states, reject. See 1 state, so DFAs can count to 1. Alpha 0 must be the start configuration. Alpha n must be an accept configuration. All these things DFAs can check. There's a unique start configuration. So you just have 4 DFAs running in parallel. You know that once you have a PDA, you can run 17,000 DFAs in parallel with it if you want. The crucial resource is the stack. So all these things, what have they checked? Yeah, I've got a sequence broken up by these hash marks. In between is a possible valid description of some configuration. But now the important thing I want to check is when going from one configuration to the next, I really followed the rules of the Turing machine and not wrote down some rubbish. Okay. For each I, alpha I goes to alpha I plus 1 according to the rules of the TN. Can I check E with a DFA? No, because I have to find the 3-cell window that has changed. It has to be in the right position. How can I tell it's in the right position? That's where I can use my stack, but I can't do that with a DFA. Can I check E with a PDA? No, because I can use the stack to check 2 successive things, right? But in the process of doing that, I'll have popped everything and I'll have moved on, and now I can't check the next pair. But I can guess where there exists I such that alpha I does not properly yield alpha I plus 1. So I can guess. So to be a valid computation, you have to check every transition. To be not a valid computation, you just have to say one place where the rules got broken. This is the crucial point. And this is why you can check complement of valcomps and not valcomps. Right? So we're going to have our PDA guess. Aha, I think this is where the breakdown happens. Okay, the DFAs have checked all the easy stuff. And it's going to say these two. I just have to show you that these two don't follow the rules, and we can prove that it's not in valcomps. So I can accept it because I'm trying to accept complement of valcomps. So is this clear? The significance of why it's complement of valcomps, just one place it has to break down. The negation of a universal, as the universal, is an existential. Okay, goody. Okay, so how do we check All right. So it's already guessed where the eye is. So it comes to this place and says, this is it. This is where the problem is going to be. It guesses okay, so in fact, before I do all that, let me explain some terminology. So note that the difference should be confined to a 3-symbol window. Three-symbol window, well, that's only finitely many possible three-symbol windows. So it's not a problem to remember that with your finite memory. You don't need the stack to remember a 3-symbol window. So what does it mean? We say 2 pairs of 3-symbol sequences are identical, are consistent if 1, they are identical, and neither one contains the head, so if you're far away from the head position, nothing should be changing when you go from one configuration to the other. Because remember, one step only changes just one cell and makes one move to the left or to the right. Or one or both contain the head and they differ according to the rules of the Turing machine. So finite state memory is enough to remember all consistent pairs. So that's equivalent to remembering all the rules of the Turing machine. And maybe there's a lot, but it's finite. You don't need your stack to do it because you don't have to count. You just have to check. Does this thing follow some rule? You can check that in the rule. Okay, so what does this thing look like? So here's some word W1. Then here is a 3-symbol window. Then here's some word W2. And then over here, we have some word W1 prime. Another 3-symbol window, which I'll call YYY. And then another okay, so the PDA stacks W1, guesses that the 3-symbol window has arrived, remembers XXX in its finite state memory, then it ignores W2. Sorry, this is a W, isn't it? Ignores W2, and then pops the stack as it reads W1 prime. Now, people have often remarked to me, maybe all kinds of rubbish happens in W1 prime and many things are broken. Doesn't matter. You just have to find one place where things are broken. It could be broken all over the place. Okay. Then it compares YYY with its stored XXX. And because it's got all the rules stored also in its finite memory, if they are not consistent, for whatever reason, I mean, you're far from the head and suddenly found that this 3-symbol window has changed, then it's not a valid computation. Or they do contain the head and you find that, yeah, there's some changes, but these are not according to the rules of the Turing machine. Reject. And if it's just complete garbage, then of course it'll find 3-symbol windows all over the place and just say, yeah, fine, I can reject. And of course, if it doesn't follow basic formatting rules, well, those have already been rejected by the DFA. So this thing is checking subtle ways in which you could be failing to be a valcomp. Then accept. Why accept? Because we're looking for things that are not valid computations. So we are done. Okay. So I have some remarks in my notes about things like people might say, hey, wait a minute, we have an algorithm to check whether the language of a context-free grammar is empty. Can't we just complement that? Well, the complement of empty is not sigma star. The complement of empty is non-empty, which is not the same as sigma star. Okay, but I want to show you a small variation. So this is called valcomps2. And I realize it's getting a bit late, but we're going to do this anyway. Valcomps2 is a variation. It looks like this. So the last one is reversed or not, depending on whether we have an odd or an even number of configurations. So you see what I've done? It's just kind of like valcomps, except I've said this and this, all consecutive pairs are reversed. So now it is easy for a PDA to check if alpha 0 gives rise to alpha 1, alpha 2 gives rise to alpha 3, because it's reversed, it's nicely stacked. You can stack alpha 0 and then alpha 1 is nicely reversed. You can easily do the comparison. Okay, but the trouble is you've now emptied the stack. Well, now you can check alpha 2 and alpha 3. You can, and so on. You can check alpha 4 to alpha 5. And then you say, that's half the job. But another PDA can check alpha 1 to alpha 2, alpha 3 to alpha 4. So valcomps2. So because it's reversed, it's actually able to check the whole configuration, not guess one place where things have gone wrong. It's checking that everything is really okay. So valcomps2 of MW, not its complement, but valcomps2 is the intersection of two CFLs. And so the halting problem can be reduced to this question. Give me 2 grammars and tell me this. If there's some string that's in both those languages, then it is a valid computation. And if it's a valid computation, if I found a valid computation, I can answer the halting problem or the acceptance problem, depending on how I set it up. Do I really require the last one to be an accept state, or so that's only a very tiny variation. Okay, so this one is of course definitely not a context-free language, but here are questions about context-free languages that you can also show undecidable. Okay, so this question is also undecidable. So you can ask yourself, which ones are CE? Okay, so the small variation at the end was a quickie, but you can see once I've shown you valcomps, how a small thing like this allows you to do valcomps2. Okay, so many questions about context-free grammars are thrown into the world of undecidability. All the corresponding questions for regular languages are decidable. All right, great. So, gosh, it's already 1:03. I'm going to stop recording.